Welcome to the Symposium Hofstadter Butterfly, and I welcome all of you also on behalf of my colleague and co-organizer Dieter Weiss. I'm really glad and happy that Doug Hofstadter, who had spent half a year in Regensburg back in 1974, 1975 as a PhD student at the physics department, returned now for the first time. Yeah, welcome back, Doug, here to Regensburg. And of course, I warmly welcome also the other speakers from abroad. That is Mikito Kushino from Osaka, Volodya Falco, who's somewhere in the audience from Manchester, and Paul Liegmann from Chicago. Thanks for coming, making the long way to Regensburg, to our university. Well, you see here on this photo this spherical symbol of the university. And this is a piece of art from 1976 from an artist, Kleinknecht, who entitled this sphere Angehaltene Bewegung. That means in English roughly stopped motion. And well, in this very year, Doug Hofstadter published also a scientific piece of art. And well, this was kind of the opposite of Angehaltene Bewegung, because vice versa, this triggered a lot of dynamics and in condensed matter and impact in the field. And what he got is what we'll see today several times, I guess, to find here the spectrum of a crystal electron in a magnetic field, and due to the form and structure of the spectrum, it's called Hofstadter butterfly, or a G-plot, as you call it, I think. Now, if we look into acknowledgements of this paper, you see that he mentioned already that most of the work or ideas have been put forward here in Regensburg while he was here. He further acknowledged a few people who played a role, particularly Gustav Obermeier and Alexander Rau, who unfortunately couldn't come, but I'm very glad that Robert Böninger, who's also mentioned here, is also with us here in the audience. And then maybe very importantly, he mentioned another collaborator. And also this collaborator is with us. It is Rumpelstilzchen here. And probably Doug will later tell us what's the root of the name Rumpelstilzchen. But thanks to Christian Ermer, who could reanimate Rumpelstilzchen from a 40-year of Dornröschenschlaf. I don't know how to translate Dornröschenschlaf into English. But it's astonishing, it's functioning again. So you can probably compute the butterfly again with the computer here. So Doug's work has been, or the seminal work has been influential and unique and also paradigmatic in various ways. So on the one hand, the spectrum that exhibits both fractal and self-similar structure had been discovered before corresponding influential work such as by Mandelbrot or Feigenbaum, that then triggered the whole field of nonlinear dynamics and led to the breakthrough, though, also in the late 70s. And moreover, it is unique in the sense that it's really a quantum fractal. Usually you would find fractals in classical physics. And on the other hand, the fact that due to Rumpelstilzchen, part of the results had been obtained numerically was at that time against practice and against thinking in theoretical physics in this aspect in the 70s. And again, this marks a shift in paradigm, a paradigm shift, since from then on, of course, computational physics, computer-aided physics took its way from the 70s until today. Now, it was as many works that followed afterwards, and I would like to mention that particularly also here in Regensburg, there are many G-plot children computed by master students, PhD students from various groups throughout the years. And I'd just like to mention a few representing all that research in Regensburg. There's Helmut Silberbauer's butterfly that from Ulrich Rössler, who's sitting there, Ulrich Rössler's group. There's also Norbert Nemec's butterfly from Giovanni Cuniberti's group. There's from Lattice QCD from Gunnar Barley's group. Here, and Rödi's butterfly, and very recently Martin Wackerl in John Schliemann's group computed also his, say, Wacker butterfly in graphene. So if we go further back into the past, we see that indeed more than 40 years passed since the fundamental works of Bloch and Landau treating the problem of an electron in a crystal or an electron in a magnetic field. And yeah, after more than 40 years, Hofstadter came and indeed computed for the first time the spectrum of the combined problem of a crystal, electron, and magnetic field. And as shown here, just marked in this histogram through the citations per year, we see that, as often with seminal works, they have a long-lasting influence. And usually a paper has a lot of citations at the beginning and then decays. Really important papers are vice versa. They show, as we see here, a still increasing number of citations. Now, we could ask if this is so important, what about experimental confirmation tests? And even this is already discussed in his paper. So he's saying, at first glance, the idea seems totally out of the range of possibility at that days. But he already suggested a way, maybe a strategy, indeed, to get into, for experiments, to get into a parameter regime where you might observe this butterfly spectrum, depending on magnetic field and energy, or suggesting two-dimensional lattices with a larger lattice spacing that helps to reach this parameter space. And I also like the last sentence here, saying this is not to say that the idea is easy, but such an intriguing spectrum deserves a good experimental test. Now, that's really true. And it took more than 25 years then that the first signatures of the butterfly have been found, and we will hear throughout the symposium a number of talks on, indeed, how can we observe the butterfly. Now, at the end of this introduction, I just would like, one might ask, why did Doug Hofstadter right now, just now, return to Regensburg? Of course, one reason is there's the occasion of the 50th anniversary of our university, but maybe also those of you who read the book Hitchhiker's Guide to Galaxy may know the true answer. The true answer is 42. It is just 42 years past since Doug Hofstadter left Regensburg in 1975. Doug, the stage is yours, please.
Okay, let's see, how do we should attach this somehow. Okay. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Okay. And 1, 2, 3, 4. That's good. Yeah. Okay. And then you'll turn it on when I tell you. Yeah. Okay. It's very flattering and a bit confusing for someone who struggled in physics for about 7 or 8 years to be the center of attention. When one feels, or I feel personally, that I was the, what's the word, I don't remember the word. Anyway, I was the lucky person who was wandering around on a beach who found a beautiful, beautiful shell. And maybe I was prepared in a certain sense to find this shell because I was sensitive to a certain kind of pattern that allowed me to sort of recognize from a distance, that's probably a beautiful shell, and so I reach down and pick it up. And then I find, 40 years later that, thousands of people have admired this shell and have written articles about it. I mean, of course, I'm calling it a shell. I suppose I should call it a butterfly. Whatever you want to call it, I feel like I was just somebody who happened to be the right person at the right place at the right time on the right beach. And so I was lucky. And so it's a bit embarrassing to be such a center of attention, but I mean, obviously one feels flattered and nice and appreciates all of that, but it sometimes feels exaggerated and a bit silly. But anyway, thank you for your interest in all of this, collectively to the physicists who have been interested in it and to people who are here to listen to these talks. So, yeah, let's go ahead. All right. So, my friend Robert Berninger, who is right there, I won't point the laser pointer at him, but my friend Robert Berninger and I grew up together, and we studied mathematics. We were fascinated by mathematics and physics jointly, both of us, and we explored questions in number theory and other things together as high school students and college students. And so at one point, it says here 1969, Robert wrote a letter asking this question. It was not addressed to me. Why doesn't number theory play any role in physics? We were so interested in both number theory and physics, and we wondered why this wonderful part of mathematics didn't seem to play a role in physics. So he wrote it to this person. And a year or two ago, this book came out. And this question was quoted in the book, and Feynman's answer to the question was quoted. Feynman, apparently his secretary kept a copy of the letter that Feynman wrote to Robert. I think Robert couldn't find the letter himself, but anyway, here's what Feynman said. He said, "I don't know why number theory does not find application in physics. We seem to need the mathematics of functions, of continuous variables, complex numbers, and abstract algebra." And so it was felt by many people, most people, that number theory had no role in physics. And that turned out not to be correct in the long run. And, I mean, not all aspects of number theory may play a role in physics, although we never know. You never know what's going to happen. So here is a one-dimensional crystal, a periodic lattice in one dimension, the integers. Number theory is about the integers. So in a sense, number theory is solid-state mathematics because it's about a one-dimensional crystal. So that's a way of thinking that maybe number theory might enter into solid-state physics. Now, I'm going to tell you a little bit about some of the number theory that I explored in the early 1960s, since what I said earlier about being prepared to recognize the beauty of a shell on the beach was that I had explored or had found some similar shells earlier, much earlier, before I was a physics student. And so I want to tell you a little bit about that. I'm going to lead up to what prepared me to be able to recognize this beautiful shell a little bit from afar. Yes, experimental. That's true. I did a lot of my explorations with the help of either a, well, I think I show it next, yeah. With the help of a very kind of electromechanical calculator that my father had in his study. He used it mostly for doing his income tax. But I used it for exploring number theory. And so I'll tell you a little bit about what I explored. I did a lot of things. I did, for several years I explored, so I'm not going to give you a big thing. But I discovered something that I gave the name of eta sequences to. And one could call them sidewalk sequences, because you imagine that there's a sidewalk whose squares are of side 1 exactly, and that you're going to take steps of size alpha. Let's assume alpha is an irrational number, such as the square root of 2, or pi, or e, it doesn't matter, cube root of 2, whatever. So you walk along down the sidewalk and you cross, how many lines do you cross every time you take a step? If your steps are of length square root of 2, of course you cross at least 1. Sometimes you cross 1 and sometimes you cross 2. So you get a mixture of 1s and 2s. And here's the picture for the square root of 2. The red dots are the positions of my toe, you could say, and so you can see that I'm crossing here 1, then 2, then 1, then 2, then 1, then 1, then 2, and so forth, and that's the sequence that you get. That is what I called an eta sequence, or if you prefer, a sidewalk sequence. And so I explored these things in great detail. It's important to point out, because I later realized that in physics this was a very an interesting, a profitable way of looking at it, that we have two. What happened? It disappeared? What happened? This is so mysterious. Is it going to disappear again while I'm not looking? I mean, it was up there, wasn't it? And it just disappeared, right? I can't figure this out. Okay. So, we have two periodic phenomena. One is got period 1, and the other is period square root of 2. The exact repetition of steps is very precise. So there are two periods that are competing with each other, or that are interfering with each other in some fashion. Okay, I gave a name to the less frequent member of this sequence. The 2 is the integer that's, well, let's just go ahead for a moment. The more frequent integer, the one that's closer to the square root of 2, because square root of 2 is 1.4 roughly, and so the closer integer is 1, and the second closest integer is 2. And those are the two integers that make up this sequence. And I called the farther one the sep, because it separates groups of what I called counds. The counds come in groups of different sizes, size 1 or size 2. But the seps always occur separatedly. They are like fence posts or something. All right, so this is another example of a different alpha. I just wanted to show it a more general case. So here the sep would be 7 and the cound would be 6, and we have a bunch of counds and then another bunch of counds and then a smaller bunch and then a larger bunch and a larger bunch. And if you count these, there are 4 of them, 4 of them, 3 of them, 4 of them, 4 of them. Now that sequence, 4, 4, 3, 4, 4, that also looks like a sequence of the same family. And in fact, it turns out that it is. Oops, what happened? Chief, this thing is so crazy. What's going on? I can't figure it out. It's like it has a will of its own. It decides for itself what it wants to show. I'm just pushing the little arrow.
I know. I think that it might be related. May I? No.
Don't worry.
But
Don't worry.
If you're only using the laser pointer, then we can do this, and you just can use those to
Yeah. Okay.
do that, and that might be safe.
Maybe it's safe. Let's hope.
Okay, so this looks like an eta sequence, another sidewalk sequence, belonging to a different step size. And in fact, that is a theorem. It's what I called the fundamental theorem of eta sequences. The lower sequence I call the derivative of the upper sequence. It's not a derivative in the sense of calculus, but it's derived from the upper sequence, so I call it a derivative. And so you can take the derivative of an eta sequence and you get another eta sequence. And you can take that sequence's derivative and you can get another eta sequence. And if your original step size is irrational, then you can keep on taking the derivatives forever. You can keep on going forever. And so the idea here, this says the derivative sequence belonging to alpha, the derivative of the eta sequence belonging to alpha is the eta sequence belonging to alpha prime, a different number, which is calculated this way. S is sep and C is count. And so in the case of the square root of 2, this would be 2 minus the square root of 2 over the square root of 2 minus 1. And if you calculate that number, it turns out to be the square root of 2 itself. So it gives itself back. And that's what happens. So what you get is alpha, then alpha prime, then alpha double prime, and so forth. For alpha, you have a count and a sep.
For alpha prime, you have a count and a sep. For alpha double prime, you have a count and a sep. So what you get is a sequence, two parallel sequences of integers, the integers that flank each of these real numbers. The two integers, one below and one above, the closest one and the second closest one. So that's what these two sequences on the left and right are. This is the counts, and this is the seps belonging to these respective numbers, the derivative, the second derivative, and so forth. All right, so in the case, and these are integers, and these are real numbers. Okay. In the case of the square root of 2, as I told you earlier, the derivative number, alpha prime, equals alpha. So this number is going down forever the same number. And so the sequence of counts is always 1. The sequence of seps is always 2. That's a peculiar fact about the square root of 2. It's a pretty fact, but it's, of course, not typical. If you can ask yourself what other numbers might have these periodic properties. Well, for example, the golden ratio phi, the golden section, has the opposite property. That is, it's the closest integer to phi, the 1 plus the square root of 5 over 2, 1.618, the golden ratio. The closest integer to that is 2, and the second closest is 1. And it turns out that phi also gives itself as its own derivative, and so you get this constant thing down here in 2's and 1's. And so it shows that the square root of 2 and the golden ratio have a kind of a complementary property. They're sort of, their two columns are interchanged. And in fact, I gave that idea of interchanging the sep column with the count column a name. I called that the function int for interchange. So the square root of 2 would be int of the golden ratio, and the golden ratio, of course, would be int of the square root of 2. They're complementary. And it turned out for every real number, for every rational number, you could calculate, for every irrational, you could calculate this thing. And I did some work using computers to plot this function. So this is the general definition. You take the counts column and the seps column, and you interchange them, and you get a new number, beta, whose the seps of beta are the counts of alpha, and vice versa. Okay. So here's what it looks like between 0 and 1. The same function reappears between 1 and 2, between 2 and 3, and so forth. It just would be up there, and then up there, and so forth. But what matters is really what happens between a pair of integers, here between 0 and 1. And you get this shape. It was very exciting to me because this was a plot that I generated over a period of time. It wasn't immediately apparent to me that it had what its structure was. And so when I actually found this shape and looked at it carefully, it was quite remarkable. It looks like it consists of what I call ribs. You could call it a rib. Here's a rib, and then another one, and another one, and another one, and another one, and they get smaller and smaller, and they go toward the corner, and then the same thing happens going in the other direction. And you could say, where is the boundary? Where is this edge point? This is at 1/2 exactly. Where is this? This would be at 1/3. This is at 1/4. This is at 1/5, and so forth. So between a quarter and a fifth, you get a little copy. Between a fifth and a sixth and a fifth, you get a copy, and so forth. And if you look at this, you can see that this rib is bent. It's a kind of a bent shape, but it gets less bent as you go towards the end. And what's really interesting, and you can see it immediately or almost immediately when you look at this graph, but it wasn't apparent when I first graphed it because I didn't graph it in such detail, is that this shape here is really a small copy of the entire thing here. It's turned 90 degrees, but aside from being rotated, this corresponds to that, And this corresponds to that. And this little rib here corresponds, or you could say, to that. And this little rib here corresponds to that, and so forth. So you are basically seeing the same structure here as you see in the whole thing. And that would mean that this also is the same structure, and then inside it there is a smaller one, and so forth. So it's nested inside itself infinitely many times, at infinitely many scales, and with different amounts of distortion, moreover. And I was able to prove this, and I was very, very thrilled with it, and I explored many, many variations on this theme. But my point is that this all happened in the early 60s. And this was pure research in number theory, experimental research, if you wish, empirical, but it was also backed up by theoretical proofs and such things. But int was a very, very central part of my life in the early 60s. I don't know what I'm doing here. I guess the reason I put this triangle here to show this is that if you look at just this half of it, you see these little copies getting smaller and smaller and smaller, vanishing towards the corner. And that's a telltale shape, or I don't know what the word would be, pattern, you might say, of something getting smaller and smaller and smaller and going towards a corner. Now, I didn't think of it at that time that way, but you'll see that this is a very important thing later. Here I've just put rectangles or squares around the copies, and inside there's a copy and so forth. I've already said this. So this I've already said. It's made of infinitely many smaller, distorted copies of itself. When I say distorted, I just mean bent, a little bit bent. Okay. Oh, this is an interesting fact. It turns out that at all irrational values, int is continuous, and at all rational values, it takes a jump. Like at, for example, a half, it jumps. It took that big jump, and at a third, and at a quarter, and so forth. So it had this curious, fascinating property that separated the rationals from the irrationals. Now, in mathematics, that makes sense. In physics, it doesn't make sense. But anyway, that was something that struck me, of course, when I was studying it. All right. Now, we jump to 1974 in Eugene, Oregon. I had struggled for several years trying to be a particle physicist as a graduate student at Eugene, and had not done anything at all. I had not been able to find a thesis topic, and it was a very difficult period of my life. And so at one point in 1974, I took a kind of a daring leap. I decided that I would jump out of my my intended field of particle physics, and go into solid state physics, which up until that time I had considered to be a very low area of physics of no importance or interest. I had thought of it as being, as we say in English, a slum of physics. I had this ridiculous prejudice, but since I had failed to get anything done in particle physics, and I wanted desperately to get a PhD, I felt I had to try a desperate move. And so I went to several physicists in the department at the University of Oregon and asked them if they had possible things to explore. And everything that they mentioned to me I couldn't relate to. But then I went to Gregory Wannier, and he said, I have 3 problems for you to consider. And he told me these 3 problems, and I don't remember what 2 of them were, but one of them, the third one that he told me about was this problem that involved crystals in magnetic fields. And so I knew that Bloch bands, this is a Bloch band. The idea is a set of energies that are all basically form a continuum, and then they end, and there's a gap, and there's a gap below and a gap above allowed energy levels. He said, okay, so what happens to a Bloch band when you put a crystal in a magnetic field? Well, when you have electrons without a crystal, you get these evenly spaced Landau levels. So that's the opposite situation. You have a magnetic field without a crystal, or you have a crystal without a magnetic field. But how did the two get reconciled when the two phenomena meet each other? That was the question. And so here is basically what we have is a magnetic field perpendicular. We don't need to consider a three-dimensional lattice. We can consider a two-dimensional lattice. The generality of the problem is preserved. And here we take a square lattice, and we take the simplest possible kind of lattice, a square lattice. And the magnetic flux per unit cell, the amount of field going through one of these cells is phi, we'll call it phi. And since there is a flux quantum that's a natural unit in physics, hc over E, we can use that to measure the flux that's going through a unit cell. And so when we take this ratio, we get this thing here. And it's a pure number. It's a dimensionless number. And it turns out that it can also be thought of as it's a pure number representing the magnetic field, but it can also be thought of as the ratio of two competing natural frequencies in this situation, or natural periods, if you wish. So in fact, it's this idea of competing natural frequencies or periodicities that we have here, and that's what this alpha happens to be. By the way, that was first pointed out to me by Felix Bloch, who was somebody that I grew up knowing very well because he was in the Stanford physics department, as was my dad, and they were very close colleagues, and I grew up knowing Felix Bloch. So it was very interesting to me that I was working on a problem that had to do with somebody who I had known ever since I was a small child. So Gregory says to me, as he's giving me this introduction to this problem, he says, it turns out that rational and irrational values of alpha act differently. And I think, surely you're joking, Mr. Wannier. Rational and irrational fields act differently. That doesn't make any sense in physics. It's not possible for something to be discontinuous, to have different behaviors at rational and irrational numbers in physics. In mathematics, anything is possible, but not in physics. Physics, the world has to be continuous, and I thought that doesn't make any sense. In case you don't recognize that fellow, that's me. Okay, so I thought rational and irrational things, that kind of reminds me vaguely of things that I've explored back in the 60s. So maybe I'll jump on board this train and see what'll happen. I didn't know what would happen, but I thought, okay, let's see what'll happen. So go for it. Okay, so let's talk a little bit about the Schrodinger equation for this situation. What one begins with is we need a Hamiltonian, and we start with the equation that represents a Bloch band, which would be this energy is a function of the two wave numbers kx and ky, where a is the lattice distance. And so this is a Bloch band. This is the wave number. Okay, now there's the classical way in which one makes a quantum mechanical Hamiltonian out of a classical expression is to replace the momentum by a momentum operator. Well, we didn't have exactly a momentum there, but we did have a wave number, k, and h bar times k can be thought of as a momentum in a crystal momentum. And so we might think, and also if you have electromagnetic fields, you add on this extra thing to the momentum, and you get this is the operator substitution that you use when you want to create a Schrodinger equation out of a classical expression. So, so if you, and we have to put in the magnetic field in order to, what I wrote, here I need this A in order, if I have a magnetic field, I need to know what the A is, and so here is the Landau gauge. This has the property that the curl of this gives you the constant magnetic field in the z direction. So what we want to do is we want to replace h bar k by this expression, the derivative h bar over I d by dx, etc., with the vector potential, as I just said. Oh, God. Okay, so here we begin with this, and then we make our substitution, which is h bar k over h. So now we have this h bar k, which we're going to guess can act like a p, or p minus e over a, e times a. So let's, here we have the thing that we want to replace it by. We're going to do this, and then we're going, this is the electromagnetic momentum, and then we're going to do a quantum mechanical substitution where we replace the p by this differential operator. And so, and then we replace the cosine by this expression, of course, in the factor of 2, we have this thing here. So we have two exponentials with this differential operator, and then we have the same thing over here, except now because the gauge has only a y component, which is proportional to x, we get a phase factor here proportional to x in both of these terms, no phase factor here. So this is the way in which this is going to be our effective Hamiltonian. Okay, now when you look at this, you may recognize that this is effectively a translation operator along the x-axis, and these are translation operators along the y-axis. So what this means is, here's the Hamiltonian, and it effectively means that we're translating, let's go back for a moment, oops. This will move us by a distance of a, right there, along the x-axis. This will move us a distance of minus a along the x-axis. This will move us a distance of a along the y-axis, and this will move us a distance of a along the other direction along the y-axis with phase factors. So here is what we get. We have the actual point that we're looking at, and then we compare it with, because we're writing the Schrodinger equation, which says that the Hamiltonian operating on the wave function gives the energy times the wave function itself. And so we've moved the E over onto this side. And so here is, we've translated plus x, plus a, minus a, I guess I can show that, and then plus a and minus a along the y-axis with phase factors. And that's, so what we get is this equation that relates the wave function at 5 points, central point, m, n. I've now changed from x and y to m and n because this is a discrete situation, and so I can label the x-axis points by ma as ma, and the y-axis is na, where n is an integer variable. So you see, we're getting back to the crystal, the number theoretical ideas. Sort of, we're kind of coming back to sidewalks in a way, two-dimensional sidewalks now. So we have these two terms here are the purple ones, these two terms here are the green ones, and then the blue one is here. And I've just made this substitution. E over E0 is a dimensionless quantity, epsilon now. And this quantity that we had before, the flux as measured in dimensionless units, is alpha. And x is ma and y is na. So that's the Schrodinger equation, but it's no longer a differential equation. It's a difference equation now. And so we can assume that maybe the variables could be separated. We could assume that we could just take this form and see what happens if we plug that in to the equation, so that we can hope to reduce the complexity of the equation from two-dimensional down to one-dimensional. And if you do that, you get, actually, it simplifies very nicely, where now this G sub m contains all the interest. This is just a periodic function of n along the y-axis, but this is a very interesting non-periodic function of m along the x-axis. And so here is the equation. Now again, this is the Schrodinger equation. Okay. So the crystal here is in the cosine, which is this periodic function. There is the crystal, and there's the magnetic field. So we actually can see the Schrodinger equation coming out of this situation, and this is the analog of the second derivative that is in the normal Schrodinger equation. There's the eigenvalue. So we can sort of see this equation as coming naturally out of the situation. And this is called Harper's equation. It was also found by Wannier in about 1955, although he never published it. So it relates just this point to its two neighbors. And so if we rewrite it in this fashion, we can say that it's a difference equation that creates gm plus 1 out of gm and gm minus 1. And it's kind of like a Fibonacci sequence. If this were a constant, then it would be very much like a Fibonacci equation. But it's not a constant. It varies because alpha, as m varies, this thing goes around and comes back to a certain value. If alpha is periodic, this will be a periodic function. So we will get a repeated value after a number of iterations. Not a repeated value of the g's, but a repeated value of this coefficient. Okay, so we can rewrite this in terms of pairs of values. So gm plus 1 gm is two values, and gm minus 1 are two values just to the left. And so this matrix is what takes this pair, and you multiply it by this matrix, and you get this next pair. So geometrically, it looks like this. Here's these two at the beginning. We multiply by A1, that matrix. Let me just go back and point this out. This is called A sub m. This is this matrix as a function of m, which is right in there. So we multiply this by that matrix, and we get this little pair. Now we multiply this pair by A2, and we get this. And we multiply this pair by the A3, and so forth. And it keeps on going out to infinity. And the question is, when will this process yield keep these values bounded? If they diverge and go to infinity, then it's a non-physical situation. But if they stay bounded, then it's a physical situation. And so that's the key question. Now, if we study, as Gregory Wannier suggested, the rational values, mathematically they're more easily tractable, more easily handleable. If we take the rational value of alpha, p over q, where p and q are integers, for example, 1/3, then it turns out that this matrix, the a's, repeat after q times. So A4 is the same as A1, A5 is the same as A2, A6 is the same as A3. So that this multiplication is the same as this one. This multiplication is the same as this one. This multiplication is the same as this one. So really what we're getting is these three together are giving us one big jump. Then these are the same, this is the same multiplication factor. A4, A5, A6 is the same as A1, A2, A3. So what we really need to think about is just this matrix, A, which is the product of these, and this is A again. So the question is, if you put A to a high power, when will this blow up, and when will it stay bounded? And Gustav Obermeier studied this carefully, and he came up with a condition on the matrix A, which was that its trace, as a function of the energy epsilon, should be less than or equal to 4. Now this matrix is a polynomial. The trace of this matrix is a polynomial in epsilon that depends upon the number alpha, of course, and so it's a polynomial of degree q, where q is the denominator of the rational numbers. So in the case of 1/3, as I just showed you earlier, it would be a cubic polynomial. In the case of 2/5, it would be a 5th degree polynomial. Now, this is not really this computer, although it's identical to it, I guess. I got this off the web. But this is my real friend. This is my actual friend, and I owe it to Christoph Ermer for having revived it, brought it out of dormancy. This was my friend in my office. And I have to say something that I learned to program when I was about 15 years old, thanks to a friend, Charlie Brenner. And I programmed very enthusiastically, as I mentioned earlier, during the early 60s when I was exploring number theory. There was a period in which I stopped programming. But I came across a computer like this in 1969. in Aspen, Colorado. And I played around with it. It had a plotter attached, and I loved it. And it was such a simple language. It was very delightful for me to program this computer. And when I was here in Regensburg, in the Lehrstuhl Obermeier, I saw a computer like this sitting on a little table right outside in the hallway, right outside my office. I saw a computer like this. I saw this computer. I shouldn't say like this. I mean, it's like itself, I suppose you could say. But I saw this actual machine sitting on a table or on a movable table outside my office, and I said to Gustav, is anybody using this? And he said, no, feel free to use it yourself. And so I took it into my office, and I started calculating I programmed it to find the value, the places where this polynomial was less than or equal to 4. And I'll tell you about that momentarily. But it's just marvelous that we have here the actual machine. This was from the web, but this is the real thing. That's wonderful. And we called it Rumpelstilzchen, I should say, Gustav. I didn't name it that. I think, I just want to be clear. Gustav called it Rumpelstilzchen because this machine wasn't, super fast. It was very easy to program and a lovely machine, but it wasn't super fast. And I had to leave it running all night. And so each morning when I would arrive at my office, I would find little values on pieces of paper like this that I would then plot by hand. And so Gustav said it was spinning gold overnight, and that's why he called it Rumpelstilzchen. So here is the polynomial for 1/3, a cubic polynomial. And a cubic polynomial can have 1 or 2 or 3 roots, but the most general case, of course, is 3. And in this case, it goes like this, goes up. Here's the x-axis. Now, we're not looking exactly what the roots are. We're looking where it is less than or equal to 4. So we have to fatten the x-axis. We make this area that goes up to +4 and down to -4. And we say, where is this function within this fat axis, the fat x-axis? And so it's coming up here, and it's in this zone that it's good. Then it goes out, and that's bad because that's where the g's go to infinity. They blow up. Now when you come back in here, they stay bounded for a little while, and then when you blow up again, and then they come back in here, and so we have 3 zones, 3 subbands for 1/3. Here's 1/5, a 5th degree polynomial. It has 5 little bands, a very tiny band here, a little one here, a little one here, so forth. Here's 2/5. Now 2/5 and 1/5 both have the denominator 5, but their structure is very different. And here there are 2 bands clustered together, then 1 isolated one, and then 2 together. Here's 1/6, where it turns out that there are 6 bands, but the 2 ones in the middle, they, as we say, kiss. They touch each other. This is one band, and then this is the other band. So we have 6 bands for 1/6. Now, I started plotting this, and this is roughly, this is not the actual plot I made. I remade this because I couldn't find the actual plot in my notebook. But basically, this is what I had in about September of 1974. And at this point, I didn't see anything happening. I didn't recognize what was going on. But in about November, I had about this much. Oops. I gave away something there, but it's okay. So I had about this much, and all of a sudden I started seeing things that I recognized, like this idea that things were going up towards a corner, getting smaller and smaller. And it looked familiar to me. And I started seeing that there might be little copies of the graph itself. In fact, there's a little copy, although you may not recognize it, between this blue line and this blue line. In other words, this blue line plays the role of that black line, and this blue line plays the role of that black line, so that this area would be a copy of the entire graph, but distorted. Similarly, here's a blue line and another blue line. They play that, they describe another copy there, and another copy there, and another copy there, and another one there, and so forth, getting smaller and smaller. And same thing happens here, but you can't really tell. It turns out that it's a much more complicated structure. But I recognized the pattern that I knew from many, many years earlier. So this was the pattern that I knew, and And then this idea that this was a copy of the graph, and this was a copy of the graph, and so forth. And so, like int, gplot, as I call it, gplot, what I guessed was made of infinitely many copies, distorted of itself. And so I presented this idea to Gustav and to Alexander Rau and to Gregory Wannier one day. And, and chance favors the prepared eye. Yes, well, I was prepared. I had done something 15 or 12 years earlier. Gregory Wannier said to me, "This is numerology," which was a big insult. He said it to me right here in this, not in this building, but on this campus. And I remember, he said, "You can do a library thesis." And I thought, what is a library thesis? Is you summarize the work of some other people. You don't do anything yourself. But if you wish, he said, you can put your numerological ideas in an appendix. Now, in a way, what can I say? What was my reaction? My reaction was very hurt, but at the same time, my confidence was not destroyed because I was so sure of myself because I recognized that pattern very definitely. So I continued with my work, and in May of 1975, after I went back to Eugene, I had access. I found a similar computer, which I called Rumpelstilzchen, using the English name. This is Homepostition, but Rumpelstilzchen was a cousin in America. And Rumpelstilzchen was, I used the same program, but it had a plotter attached. And the plotter allowed me to generate this graph. And that's what I found in May of 1975. And I showed it to Gregory, and he still didn't understand it. And he still wanted me to, he still didn't believe my ideas. But what I did was, I took a little area down here, between about a 6th and a 7th, something around here, where I knew there was a copy, but you couldn't see it because it's so tiny. And I had Rumpelstilzchen blow this area up and what I called rectangularize it. There it is when you rectangularize it. That's the structure inside there. And of course, he could see that it was basically the same. And he came around in about August of 1975. It took about almost a year for him to understand these ideas. Now, what about irrational values? Well, it turns out you can approximate, of course, an irrational by a sequence of rational values. And when you do this, you get bands inside bands, inside bands, inside bands. But if it never stops, then you never really get bands. All you get is points at the end. So it's a Cantor set. What is a Cantor set? Well, the most classical one, invented by Cantor, begins with a full interval, and then you take out the middle third. You just eliminate. And now you do the same thing to these. So you take out the middle third of those. And you keep on doing it. And what you wind up with in the end is something that's very sparse. But does something remain in the end? Yes. Infinitely many points, in fact, uncountably many points remain at the end. But it's measure zero set. And so that's what the spectrum is, and what I was able to demonstrate in my thesis is the case for an irrational value. For a rational value, it's a set of small bands. Each irrational has a different Cantor set. How does one reconcile this with physical reality? Well, the idea is that in any real situation, the magnetic field is not determined to infinitely many decimal places. It's only known to some degree. And so effectively, you're really combining a bunch of fields that are near each other. And so I just took the union of the spectrum for a bunch of different values of the magnetic field. I visited Feynman in his office in 1975, in the summer of 1975, and I was showing him this idea, and he liked the idea, and he said, "Oh, you jiggle the graph a little bit. Depending on how much your uncertainty in the magnetic field is, you jiggle it either a lot or just a little tiny bit, or if you know the magnetic field to infinitely many places, then you don't jiggle it at all." But that was his phrase. And so here's what, if you jiggle it a lot and it's not very, in other words, the magnetic field is not well determined, then you get this structure which is completely continuous. You see no trace of any fractal structure, any copies of itself anywhere. All you see is this, this thing. If you jiggle it less, so you know the magnetic field more accurately, then you get more detail. And if you jiggle it less, then you keep on getting visible, you start to be able to see more and more detail. And of course, this is if you jiggle it 0. So this was my graph, and in my PhD thesis, I wound up putting it on page 137. So I guess I really was a numerologist after all, as Gregory had said. Here I will conclude with a poem. What happens if a crystal's laced with the lines of a magnetic field? What spectrum will the world be graced with? What energies will nature yield? It turns out that the matter's crux is determined by how great the flux is. P over Q, Q bands begets. Non-ratios, though, give Cantor sets. On hearing this, a physicist will declare it numerology. But once shown G-plot, all agree deep magic's lurking in a crystal. This gem I found by luck, that's why, there but for G-plot's grace go I. Thank you.
Thanks a lot, Doug, for this fascinating view back to the 70s and 60s and the discovery. We have time for a few questions. Maybe, yeah.
Well, I'll talk loud.
Let's see whether there are questions.
I'll just hold this. Go ahead.
There's one in the rear pod.
So you mentioned that thank you. You mentioned that luck helps the trained eye. How would you advise us youngsters to train our eyes?
Well, you know, I don't know that I could advise anyone, but I would say that I can, if you allow me to just use my own personal case as a sample that might give you a suggestion implicitly. When I was an undergraduate, everything that I studied came out of a love for beauty. All of those questions that I asked myself in number theory were all driven by passion for beauty and exploring the nature of mathematical beauty. And I would also say that, rightly or wrongly, when I went to physics in the late 60s and had this prejudice about particle physics being the only worthwhile part of physics, a very silly prejudice, but I had that prejudice. I found myself struggling against ideas in particle physics that I thought were ugly. And the ugliness repelled me so much that I couldn't find anything in particle physics that meant anything to me. And so in the end, as I said, after 6 or so years of bashing my head against the wall of particle physics, I took this desperate leap into a different area. But, and again, I came back. I was just lucky that Gregory Wannier was in Oregon and that he had this problem and so forth. I came back and I was attracted by these words that he gave to me in his introduction of this problem, rational and irrational magnetic fields. And I said, that reminds me of stuff that I explored when I was much younger and stuff that I thought was extremely beautiful, in contrast to all the stuff that, you know, I had hated in particle physics. So I can't give any advice, but my own personal experience was just always pursue what you consider to be the pinnacles of beauty. That's what, you know, for me, was the trick. That's all I can say. No recipes.
I think there's a question in the rear again.
My question aims at the description of infinity. Would you say that the butterfly, consisting of an infinite number of copies of itself, first gives proof that there is an idea of infinity which exists in real life, and second, provides an idea which even may be kind of like of a universal concept?
Well, the butterfly is a mathematical structure. It comes out of mathematical equations, out of a difference equation that involves the behavior of a system that, in theory, has an infinitely long decimal expansion, just like pi. You know, pi is, well, every number has an infinitely long decimal expansion. Even 1/3 is 0.333333, infinitely long. I mean, in mathematics, we're used to dealing with things that are, in theory, infinite. Not just the butterfly, but, you know, just numbers with infinitely many digits. We take that for granted. The square root of 2 has an infinite decimal expansion, so does pi. However, when we come to the real physical world, we don't ever deal with things that are infinite. The universe doesn't seem to be infinite. The structures that things are made of don't seem to be infinitely small. The universe is not infinitely big, and so forth. I mean, maybe time goes on forever. I wouldn't know. But all I can say is that in mathematics we deal with infinite things fairly comfortably. We say there are infinitely many prime numbers and so forth. In mathematics, which is part of reality, I mean, it is part of reality, but it's only a small part of reality. And in most of the world that we deal with, I don't see infinity as actually playing a role. So that's an attempt to answer this question.
Okay, hello. I have a technical question about your numerically, your experience in number theory. I guess that is what you explained to us is self-similarity, or that this can be explained with the continued fraction expansion of this alpha, of this number. Is this true? First question.
It's certainly related to the continued fraction. There are different types of continued fractions. The kind of continued fraction that seems to be the most relevant in this case is not this standard thing called a simple continued fraction, but something called nearest integer continued fraction, studied or discussed in a book by Perron called Nach nächsten Ganzen Kettenbrüche. It's related. It's a similar phenomenon. But it's a little bit different than normal.
And the second question is, of course, whether this butterfly feature is this also related in the same way to continue or next?
Well, yeah. The copies of the butterfly are located in the same. How to say it? I can't say the same place, but in some sense that it determined where the copies of the butterfly are located is determined in the same way in both int and g-plot, or the butterfly. Between, for example, the most fundamental copies are between 1/n and 1/n+1, like a quarter and a fifth, or a fifth and a sixth. The fundamental copies are always located in those same spots as for int. But it's a much more complicated structure than int. And in fact, it's curious, many mathematicians have worked for many years in trying to understand the properties of this spectrum. I mean, it's been a very long and arduous struggle to understand the spectrum of of the Harper's equation. And recently, some major progress has been made, I don't know, a few years ago, and by Artur Avila and, what was her name? I can't remember her name, a Russian mathematician. And the two of them did work and proved that for almost all irrational values, it is a Cantor set.
Okay, I think we will move on now to the next talk. Thanks again, Doug.
Thanks.
Great talk.
there is one last thing for today that Professor Douglas Hofstadter has asked me to show all of you. And somehow I wish more of you could have seen this, of the audience who were here this morning. It is a picture from old times in Regensburg, and it is yet another striking example of self-similarity if you look at the picture, and especially if you look at Douglas Hofstadter today. Could you please come up to the stage and make a few comments about that very picture as closing remark for this wonderful session?
Yeah, well, I deliberately wore this sweater today. This was the sweater that I wore all the time in Regensburg back in 1974-75, and I thought I had this picture in my talk. I was expecting it to come up sometime in my talk, which I formulated a few months ago, and I guess I left it out, and so I really wanted to ask you to put this up. Anyway, this is a lovely picture. There's Gregory Wannier on the right, Gustav Obermeier, who so generously hosted me in his laboratory, Alexander Rau, who we wish could have been here today, who was such a remarkable contributor to all of these things, and then myself, age either 29 or 30, depending on which time of that my stay it was taken at. So this was a difficult period of my life, but at the same time it was a very rich period of my life, and it's so interesting to be back in Regensburg after, as we say, 42 years. And believe me, I don't know if you can understand this, but it's so weird. It is so weird to hear your name thrown around over and over and over and over and over and over again, when you feel like you made the tiniest contribution by picking up a shell on the beach. And you picked up the shell, and then 1 million people admired it, and it's very bizarre. It's psychologically weird. It's pleasant, but at the same time extremely embarrassing and confusing. But I do appreciate the fact that, let me say, I appreciate the fact that I was so lucky to be on that beach at that time, right here in Regensburg with my friend, and thanks to my friend Rumpelstilzchen. That's it. Thank you.
Ja, ich glaube, das waren perfekte, oh, maybe I should talk in English here. I think these were perfect words to end this little but very beautiful conference. Thanks for all the contributions. And just a very little announcement, there is another public talk this afternoon by Theo Geisel at 5, as you all may know already. Thank you very much.